All right. So picking up where we left off, top-down processing is a vital skill for understanding written language. So remember, our brain tries to find meaning, and our vast experience with reading is probably our best asset for our reading ability. We read what we expect to read. Those two examples where the extra the was added in there, most people are going to skip right over one of those thes without even noticing it. We read what we expect to read. So, written language, this skill is heavily influenced by top down processing. It's almost completely dependent on it. So, let's talk about what happens in the brain when we read a word out loud. What neural pieces of anatomy are involved? How does information flow through the brain when we want to read a word and speak it out loud? Well, we're going to start with the visual cortex. So we're looking at a piece of paper with some words on it, and that information travels through our retina, through the optic nerve, back to the visual cortex, and this is where those letters are transformed into a visual code. And turns out we are actually tuned to recognize words. There's a certain part of our visual cortex that is specifically sensitive to words. They kind of stand out in our visual field. And maybe you've experienced this phenomenon if you've ever been driving and you see like a large billboard with some pretty big words on it. It kind of grabs your attention. We can't help but read those words. It's almost impossible not to. This is because our visual cortex is very sensitive to words. They kind of jump out at us. Turns out we're not the only species on the planet that has this sensitivity to words, or at least the ability to be sensitive to words. Baboons have this ability as well. I've got a short video on the Canvas course website if you want to check that out. So, information gets into the visual cortex. Physical letters are turned into visual information. That visual information is then sent to the angular gyrus. And if we can get to the next slide here, there we go. The angular gyrus is a small little chunk of cortex that is located between the visual cortex and the auditory cortex. The angular gyrus plays a very important role in this process. The angular gyrus is going to take that visual information and transform it into auditory information or auditory code. So it changes sight to sound. Now, the angular gyrus plays a very important role in the disorder of dyslexia. In people who suffer from dyslexia, the angular gyrus is going to be less active. There's going to be less action potentials going on in the angular gyrus. So normal readers, people who don't suffer from dyslexia, they will have a very active angular gyrus while they're reading. People who do suffer from dyslexia, the angular gyrus is going to be much less active. So the angular gyrus takes that visual information, that sight information, turns it into sound information, and then passes that sound information onto Wernicke's area, which is the next part of the process. In Wernicke's area, this is where that sound information is transformed into language information. So an auditory code is transformed into a linguistic code. So remember Wernicke's area, this is where Carl Wernicke's patient had pretty severe damage and was no longer able to produce comprehensible speech. The words were understandable, but they made no sense. So in Wernicke's area, this is where sound is transformed into language. If you have damage here, just like Carl Wernicke's patient did, you will have nonsense speech. Again, it is understandable, but it makes no sense. Spence? Makes no sense. Once the Wernicke's area is done transforming sound to language information, then that language information is sent on to Broca's area. Broca's area is where that language information is transformed into a speech plan, a pronunciation code. So remember, Paul Broca's patient Tan had damage to this area of their brain, and during Tan's lifetime, he could only produce that one word, tan, tan, tan. Damage here results in an inability to produce speech correctly. So Broca's area takes language information from Wernicke's area, turns it into a speech plan. Basically a plan for how our articulators, like our lips and our tongue, are going to produce whatever word it is that we're about to speak. So Broca's area turns language information into speech information, pronunciation information, you could call it, and it sends that information on to the motor cortex. And their motor cortex is where we actually have conscious control over our articulators, our muscle movements, our voluntary muscle movements. So this is where we're able to form our lips, put our tongue in the right place in our mouth, position all of our other articulators correctly, and we can make speech. We turn a speech plan into actual speech. All right, so there's a lot of steps here. Information has to travel pretty far across large areas of the brain before we can read a word out loud. So let's kind of recap here. Starting with the first step here, the visual cortex. This is where written words on a piece of paper or a screen are turned into visual information. That visual information is sent on to the second step, which is the angular gyrus. And this is where visual information is turned into sound information, auditory information. The angular gyrus passes that information on to Wernicke's area in the temporal lobe, and Wernicke's area turns sound information into language information. And Wernicke's area passes that language information onto Broca's area. Broca's area is where that language information is turned into pronunciation information. And then that pronunciation code is sent on to the motor cortex, which is the fifth and final stop here. The motor cortex is where we have voluntary control over our motor movements, and a word can be spoken. All right. So let's talk briefly about dyslexia. Dyslexia has been misrepresented over the years, and it's important to understand that dyslexia is not a vision disorder, it is not an auditory disorder, it is not an intelligence disorder. It is an information processing disorder, and that's an important distinction to make. One of the common ways that you'll see dyslexia portrayed in movie or TV shows, that is people will say, "Oh, I just get the letters mixed up. I can't tell the difference. It all looks the same to me." Well, that's not a totally accurate portrayal of dyslexia. That is sometimes a symptom, but it's usually not the most common. So an information processing disorder, what does that mean? This is when people have difficulties interpreting written characters into sounds. Just remember back to the angular gyrus that I was talking about. That's a very important piece of this puzzle here. For whatever reason, the angular gyrus is not properly translating visual information into sound information. So the cause of this can be varied. It usually points to difficulties or impairments in the angular gyrus, but the reason for this can come from a couple different sources. This could be neurological, meaning there could be trauma, whether that's a stroke or actual blunt force trauma to the head. That can damage the angular gyrus. There could be a genetic disorder where the angular gyrus just doesn't develop fully, doesn't develop properly. It might not be getting all the things that it needs to thrive. And there is also a third category here, and this would be early exposure. It's kind of one of those things where if you don't use it, you lose it kind of thing. If children don't have enough early exposure to reading, either from a parent or guardian or maybe on their own, then the angular gyrus just doesn't get the training that it needs to develop into a healthy, developed way. This is one of the reasons that if a child is really struggling with reading early on in their life, they are usually heavily encouraged by healthcare professionals to increase what's known as lap time, where the kid is actually sitting on your lap, you're reading a book together, usually reading a book that's at their reading level, and you're kind of helping them with the pronunciation. So currently, the best approach we have right now to treating dyslexia is to catch it early, provide extra learning aids, so provide extra help for those kids that are struggling. And usually, this type of specialized learning can overcome early deficits. As long as we catch it early and as long as that extra learning is provided. So that means that extra learning is provided in a school setting and outside of a school setting. But again, if those two things are done, then those early deficits can be wiped out later on. I want to finish this language unit by talking about animal language. This is a very common thing that students like to talk about. It's a pretty exciting thing. The idea that, animals, non-human animals, could have language. The ability to communicate or speak with another species it's just an exciting thing to do. It just sounds fun. So researchers, psycholinguists, linguists, philosophers even have debated a lot about what exactly human language is. And it's really hard to come to a consensus on anything, but a lot of people would say that language consists of 5 key attributes, and those 5 attributes are listed on this slide here. And I'm going to start at the bottom and work my way to the top. So I'm going to start with displacement. Displacement is the ability to refer to an object that is outside of our immediate vicinity. So language meets this requirement, this attribute of displacement, because you and I can talk about things that are not in our direct field of vision. We can talk about the planet Mars. We can talk about people on the other side of the world in China or Australia or New Zealand. Those people are not in our immediate vicinity, but we still have the ability to talk about them. We can also talk about abstract concepts like ideas, emotions. Those are not necessarily things that are in our immediate vicinity. So a language, in order to be a language, or in order for someone or an animal to have language abilities, they have to show some ability to talk about things that are not in their immediate vicinity. Animals do have this ability. The next one there, moving up from displacement, is arbitrariness, meaning there is no inherent relationship between a symbol and its meaning. The example that I gave in the last lecture was the relationship between the word cat and what a cat is. So that's arbitrary. Animals do understand this, that there is no inherent relationship between a symbol and what that symbol is referring to. So yes, animals meet this attribute of language. Moving up to semanticity. This means that specific meaning are attributed to specific symbols. This is just basically saying, can they understand that there is a relationship between a symbol and what that symbol is referring to? And this one's pretty straightforward. Yes, animals can understand that individual words are referring to specific things. So those 3 language attributes at the bottom there, displacement, arbitrariness, and semanticity, non-human animals have the ability to grasp these different attributes. But the last 2 attributes at the top of the slide there, This is where humans kind of set themselves apart. This is where animals just seem to not fully understand language. So we're going to start with generativity. Generativity is the ability to produce and comprehend new sentences. What I mean by new sentences, these are sentences that the speaker, the language learner, has never heard before. So you or I have the ability to produce completely novel sentences, sentences that you or I have never encountered in our life. That perhaps have never even been spoken in human history before. We have this ability of generativity. If you think about, every book that has ever been written, a sentence really only has to be about 8 or 9 words long for it to have a very good chance of never having been spoken before in human history. So we have this ability. Non-human animals don't quite have it. They have something that approaches it, and we'll talk about some examples on the next slide here. And the last one here, and this one is firmly only in the human side of the ring, and that is syntax, complex grammar. There's no example anywhere on the planet or anywhere in history of people who've researched this that animals can grasp a complex grammar. So those two things at the top, those two attributes of language, syntax and generativity, so the ability to understand complex grammar and then the ability to generate new sentences never heard before, those are the two attributes of language that seem to be specific to humanity. Non-human animals can understand semanticity, arbitrariness, and displacement, but those are sort of rudimentary foundational building blocks of language. So some examples here. Nim Chimpsky. This is a play on words of Noam Chomsky. So some researchers decided they wanted to prove B.F. Skinner right and Noam Chomsky wrong. So they kind of agreed with Skinner that you could teach an animal language through the principles of reinforcement and punishment. And they sunk quite a few years into this project. And unfortunately, the chimpanzee, who they named Nim Chimpsky, just never quite fully developed language. Nim Chimpsky learned 125 signs in American Sign Language, but Nim never showed any ability for complex grammar. Nim would just repeat words over and over again. If Nim wanted grapes, he would say grapes, 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 now, now, want grapes, now, grapes, now. That's kind of like what you would expect a 1 or 2-year-old to say. And it's a far stretch to say that a 1 or 2-year-old has full language abilities. So Nim Chimpsky never developed complex grammar, never quite reached that human threshold of language. Alex the parrot, Alex was a gray parrot, had a huge vocabulary, learned over 100 different words, could produce them, could recognize them, but once again, Alex the parrot never really strung words together. He could put 1 or 2 word strings together, but never anything resembling a complex grammar. And another example of animal language there, honeybees. Honeybees have been known to dance, and this type of dance allows them to communicate to other bees in their community where the location of food is. So that would be an example of displacement. Those honeybees can talk about something that is not in their immediate vicinity. So this will be my final slide here. And just to kind of put this in context, just because a human can jump, do you say we can fly? Just because non-human animals have a few aspects of human language, do you say it has language? And that's kind of what it comes down to. Yes, there are some very impressive language-like abilities that animals have. There's some very impressive communication skills that animals have. But what they have is not language. Language is unique. Language is special. It's very, very, very complex. And it's something that appears to be it's only in the realm of humanity. It's not outside of that realm. And that is all I have to say on that. That is the end of our language unit. Thank you for listening. Let's get this thing ended.